Hello and good morning, everybody. We're going to start talking about 6.1. You'll have to excuse my handwriting. I'm still getting used to this thing here. It's called, this is another matrix session, and this is the first of our real pre-calc matrix sections. This is multivariable linear systems and row operations. And this is going to get not just somewhat, but pretty tedious, but it is the foundation of how matrices are truly done, so we really need to talk about it. And the first thing that we're going to talk about is something called Gaussian elimination. So I'm going to give you some information about Gaussian elimination, and then we're going to do an example as we tend to do. In Gaussian elimination, we're going to use row operations. We see that term again, and I am going to give you more information. You're going to see what row operations look like, but for now, I'm just going to start using the term, and we'll get more familiar with it as we go. We're going to use row operations to put an augmented matrix into row echelon form. Row echelon form is a form. We're going to have this weird matrix that kind of looks like that, and I'm going to go over what it has more later. But row echelon form looks like this. The diagonals, and it could be more than a three variable system, but we're mostly going to work in three variable systems here. Row echelon form is going to have a bunch of numbers where I'm putting the question marks, and then ones along the diagonal, and beneath the ones, zeros. And that's what we call row echelon form. And the idea is we're going to have to use what's called row operations to take an initial matrix that we're going to set up from a system of equations, a system of linear equations, and we are going to work it until it looks like this. And so that's what we're going to do in the example coming up on the next page. So let me add a page here, and we'll see if we can work an example. This is all coming off of the 6-1 study guide, which once I've done it will be linked in PowerSchool in the assignment. So our example for Gaussian elimination, this would be example 1, is to solve by Gaussian let me write that a little bit clearer. Solve by Gaussian elimination the following systems of equations. So we're going to solve x minus 2y plus z equals -1. That's going to be the first equation, and then 2x plus y minus 3z equals -7 is the second equation, and then 3x minus y plus 2z equals 0. Now, remember how we used to do these back in old Algebra 2? We would take a two-variable system, and we would use elimination or substitution to narrow down what we have and solve for one of the variables and plug in for the other one and resolve for that one. But as we get into three variables and larger, I think you can see just by looking at this, imagine trying to set it up so that you would get all the elimination that you need, or imagine trying to do all the substitution. It would be three different substitutions, and you'd have to do it multiple times and all this weird stuff. So instead of that, we're going to use this matrix method of Gaussian elimination, and there's going to be some tediousness to it, but you're going to see that if you take it one step at a time, it's fairly simple. So what I'm going to do is, as I love to do, I'm going to change all these minuses to plus negative. That's a negative y right there. Change all the minuses to plus negative, and I'm going to create what is called the augmented matrix based on this. And the way this is going to work is this is going to be column X. We're going to have a column X, a column Y, a column Z. They don't usually get labeled that way. I'm just labeling them for demonstration purposes. And then an answers column. And what we're going to do is we're just going to put in the coefficients, the numbers attached to the variables in each one. So like for the first column, all the x's, the first coefficient is 1, the next is 2, the next is 3. In the y's, it's -2, and then 1, and then -1. This, by the way, is the main reason that I changed all the minuses to plus negative, so I would make sure that I would write all the numbers positive and negative correctly. So in the z's, we got 1, -3, and 2, and then my answers are -1, -7, and 0. And it does make it is important to make sure that each of the equations lines up, that you're using one equation straight across in every row. Okay? It doesn't matter which row you put them in, but it does matter that you stay consistent on this row has nothing but the numbers for this equation. Okay? So now we have to get into the very tedious row operation parts, and the way these row operations work is, so let me rewrite this augmented matrix here. And what's going to happen is I'm going to take the first row needs to have a 1 at the beginning. And that's all I care about for the first row. So as you can see, the first row is done because I already have that 1. Okay. So I already have that 1. But then I want to have a 0. I want that 2 to become a 0. And the way that I'm going to make that happen is I'm going to do some stuff that's going to happen sort of inside of it, sort of in your head, to make that happen. For example, if I do negative 2 times row 1 plus row 2. What will happen there is I would be multiplying this entire row by negative 2, okay? And then I would add it to that row, and if I do that, I do negative 2 times 1 is negative 2, and negative 2 plus 2 gives me 0 for that new row 2. Now, I'm doing all this, but I'm only going to change row 2. For row 1, I'm going to do it and then immediately undo it. Because it's an equation, as long as I multiply everything by this negative 2, I can then divide everything by that negative 2, and it essentially will look like I haven't used it, okay? So I'm going to recopy the original row 1 here. And I'm working on changing row 2, okay? So this is only going to change row 2. In fact, row 3 I'm not working on yet, so I can copy that as well. So if I do negative 2 times 1, I get negative 2, and negative 2 plus 2 gives me that 0. And then negative 2 times negative 2 gives me positive 4, and positive 4 plus the 1 underneath it gives me a new one of 5, okay? And then negative 2 times that 1 gives me negative 2, and negative 2 plus negative 3 gives me negative 5. And then finally, I multiply by the answer. Negative 2 times negative 1 is positive 2, and positive 2 plus negative 7 gives me negative 5. So now I've got a new matrix with a 0 in the right place. I'm going to start a new board here, and we're going to need to, I'm going to recopy what I've done so far. So now I've got this new matrix. That's probably not big enough. Now I've got this new matrix. It was still 1, negative 2, 1, and negative 1. And then I've got the new row 2, 0, 5, negative 5, negative 5 again. And then my row 3 stayed the same, 3, negative 1, 2, and 0. So there's my new matrix. Now the next goal is that this number here becomes a 1. So the way you do that is you just do a simple multiplication. You multiply by the reciprocal of that number. So what I'm going to do is I'm going to take 1/5, because 1/5 times 5 is 1, and I'm going to multiply it by row 2. And that's going to give me a new matrix. It will not change row 1. Remember, row 1 I'm done with, I'm okay with. It will change row 2. 1/5 times 0 is still 0, and remember, I want a 0 there. 1/5 times 5 gives me that 1 that I wanted. 1/5 times negative 5 winds up giving me negative 1, and that's okay. That what that number is whatever it is. That doesn't really matter. And then 1/5 times negative 5 is negative 1. So what I did was I took all of this and multiplied it by 1/5. To get my new row 2. Row 3, again, has not changed. So now I've got a 1 here, a 0 here, and a 1 here, and that is what I'm looking for. I'm looking to have that pattern emerge. The next thing to have happen, oops, not there. The next thing to have happen is that I have to use row operations to make this a 0 and that a 0. And then I'll take whatever that final thing is and I'll turn it into a 1. But I have to make the zeros first. Okay? So let me get rid of all those arrows and all those circles. And let's work on making that 3 a 0. So to make that 3 a 0, let's start a new row operation. The easiest way to make that 3 a 0 is to take the top row, multiply it by -3, so -3 times row 1, and add it to row 3. And what happens if I do that is, again, these rows are not going to change. Essentially, I'm going to do something to row 1 and then immediately undo it. So I'm not going to write anything different for row 1. Row 2 I'm not even looking at yet. And then row 3 is the one that starts to change. So I'm taking row 1, multiplying it by -3, and adding those new numbers to row 3 to create a new row 3. So -3 times 1 is -3. -3 plus 3 is 0. That was the actual goal. And then -3 times -2 is +6. And 6 plus -1 is 5. And then -3 times 1 is -3, and -3 plus 2 is -1, and then finally -3 times -1 is +3, and 3 plus 0 is 3. So I have a new matrix again, and that is the next thing that we care about. So I'm going to take that to a new board, and I'll recopy that new matrix that we want. So we've got 1, -2, 1, and -1 as the first row, and that's never going to change now. 0, 1, -1, and -1 as my second row. And my new third row, 0, 5, -1, and 3. And so now I want to take this 5 right here, and I want it to become a 0. Okay? So that's my next big goal. I'm going to get rid of that so we can look at it a little cleaner again. But that's my next big goal. So I need another row operation to do that. And the simplest way to do that is to take row 2 now, and if I multiply row 2 by -5, if I do -5 times row 2 and add it to row 3, I will get a new row 3, and I won't muck up the last row 3. I will keep that 0 in the front of it by using this technique. So my row 1 stays the same, nothing's happening to it, I'm not even using it this time. My row 2, I'm going to multiply by that -5, but then I'm going to immediately undo that because I want it to still look like this. And we're totally allowed to do that, because remember, these are equations. If I do something, I can undo that thing. And then I got to make my new row 3. So if I do -5 times 0, that's still 0. 0 plus 0 is 0. If I do -5 times 1, that's -5. and then negative 5 plus 5 is 0, and that was my big goal, to get a 0 there, to get a 0 and then another 0 for that third row. And then whatever happens here, we do negative 5 times negative 1, which is positive 5, plus negative 1 winds up being positive 4. That's not a very good 4. And then finally, negative 5 times negative 1 is positive 5. 5 plus 3 is 8. And so I have my new stuff, and now all that's left is to make that 4 a 1. So that's my next goal, is to make that 4 a 1. I'm going to get rid of that now. Make it look a little bit cleaner. And all I need to do that without messing up the zeros is to multiply that third row by 1/4. So if I do 1/4 times row 3, I'll get a new row 3, and of course I'm not changing anything about rows 1 and 2. So I'm multiplying this third row by 1/4, and if you multiply it by 0, you get 0, and if you multiply it by 0, you get 0, and then 1/4 times 4 is 4 times 1 over 4, which is 4 over 4, which is 1. And that was the goal, to make that 4 into a 1. And then I have to do this last one, 1/4 times 8 is 8 times 1 over 4, which is 8 over 4, which is 2. Okay. So now this is what we call row echelon. Oh, that looked awful. Row echelon form. And that was our goal, was to put it in row echelon form. Now, how does that help us solve the actual equation? Well, it gives us new equations to deal with. So let me start that on a new page. I'll write this row echelon form matrix one more time so that we can look at it here. 1, negative 2, 1, negative 1 for our first one, representing our first equation, and then 0, 1, negative 1, negative 1 representing our second equation, and 0, 0, 1, 2 representing our third equation. So I want to focus on that third equation. What this means is these numbers tell us, remember again, this was the X column, the Y column, the Z column, and the answers column. And because of that, I can rewrite these in equation form. I have 1x, which is just x, plus negative 2y plus 1z, which is just z, equals negative 1. I have 0x, which means 0 times x, so it's 0, and so I don't have to write it, plus 1y, so that's just y, plus negative 1z, or just negative z, equals negative 1. And then I have 0x and 0y, so I don't have to write either one of those. And then I have 1z, or just a z, equals 2. So the reason this works so well is because you get one answer for one of the variables, this one right here. I got z equals 2, and I am able to then take that and plug that in the equation above it. So now I can write 1 plus, or y plus negative z, but z is now 2, so it's negative 2 equals negative 1, and now I can solve for y. So I can add 2 to both sides, and I can get that y equals negative 1 plus 2, which is positive 1. And because of that, so now I have z equals 2, I have y equals 1, and so in this final equation, I have x plus negative 2 times y, which I know now is 1, plus z, which I know now is 2, equals negative 1. And so because of that, I can solve this. And so that's what I'm going to try and do here. I've got x plus, this will be negative 2 plus 2 equals negative 1, and then that winds up, negative 2 plus 2 winds up being 0, so I can ignore that. So I actually get, this one turned out to be really easy, I actually get that x equals negative 1 here. So now I've got the answer to all three variables. And if we imagine that this was being done on a three-dimensional graph, 3 variables, 3 dimensions, then I have these 3 values can represent a point on that 3-dimensional graph of negative 1, 1, 2. Okay, so that is how you use Gaussian elimination to solve a 3-variable linear system, which you are going to see in a few problems that I'm going to ask you to do. One little note, if missing a variable, use a 0 placeholder. Okay, so that's Gaussian elimination. I'm going to make a separate video for Gauss-Jordan elimination. So thank you for watching the example on Gaussian elimination.